Bum 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 bum. All right, welcome you guys back to Science in Pajamas. Today we're going to be talking about a form of biotechnology called gel electrophoresis. Now, this is a pretty cool technology because what it allows you to do is compare samples of DNA. Now, before we show you some examples, if you've ever watched, those crime shows or movies or, things like that, they take the DNA from one person and then they um, compare it, like, okay, are they the father? Are they the bad guy? That's what gel electrophoresis does. So running the DNA is exactly what this process is. Now we're going to talk about how to do it, and I'll even show you some hand-drawn examples because I don't exactly have access to that technology while in my own home. All right, so first off, you have your DNA, your genetic material. So imagine that line is your DNA. Now, what the first step is, essentially you're going to add these things called restrictive enzymes. And what they do is they're going to search out certain sequences of bases and they're going to chop the DNA. So, pew, 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 pew. So now we have all these pieces of DNA. Now that's very, very important. It's going to cut some of these in slightly different places in different people, which is why we can use these to make comparisons. Now, if you notice, they're all different sizes, and that's actually very important for when we read and analyze this process. So I'm going to leave that up there. We are going to come back to that. So how this works is you have this gel, hence why we call it gel electrophoresis. It's usually in this little specialized container, and that is in a larger container. You're going to put some liquid in there just to barely cover it up, and you're also going to end up running an electric current through there. So we have our negative side on this side and the positive side on that side. All right. So what happens is you're going to have these little wells, these little tiny openings on the side of the gel that is usually closest to the negative side, if I remember correctly. And in each one of those little wells, you're going to put a sample of DNA. Now, it's going to typically come from different sources. So, for instance, if I want to compare, we've all seen, those trashy shows where it's like, who the baby daddy? So we can put the baby's DNA in one of the slots, and we can put potential dads in each of the others. Now, remember how we said we cut the DNA? That's actually really important. So let's say this is baby's DNA. See how there's different sizes? Well, that's going to determine how far the current can drag those fragments down. Because once the current goes through the gel, the current is going to cause the DNA that we put in here to be pulled with the current to the positive end. Now, how that works, or how far it's able to drag the fragment, is dependent on the size. Think of it this way. Imagine, I give you, I'm going to draw you in red. So there's you, and I ask you to carry a 100-pound bag on your back. How far can you move that bag? Well, depending on each individual person, probably not that far. Some, yes, more than others. I'm sure some kids watching this are like, well, I can carry that quite a bit. That's okay. Not everyone can. So a heavier bag is going to be harder for you to move. You won't be able to move it that far. But what if instead I gave you a 1 pound bag to carry on your back? How far can you carry it? Pretty far, right? It's the same idea with these. These larger sections aren't going to be able to be pulled as far down the DNA, down the gel. The smaller fragments can be pulled much farther. So what I'm going to do is I'm going to kind of label these a little bit. Obviously the electric current will take care of this, but just so you can see. So this is the biggest. Then this one and this one. They're very close in size, but that one's a little bit bigger. Then this one. Then 4. This one. And 6 and 7 look like they're almost the same size. So 1 is the biggest. Maybe that only gets pulled this far. And then we have 2 and 3. 2 is a little bit bigger than 3, so we're going to see 2 lines very close to each other. And then we have, 2, 3, 4 is a little bit smaller. 5 is quite a bit smaller, so that's going to be way down there. And then, 6 and 7 are very close in size again. And then we would do that with all the other DNA. So let's say another sample might look like this. And now notice they're all a little bit different. There are some similarities, there are some that are the same, but they're all different. This is why we can use this process to identify identify individuals or compare them. Now, another interesting thing, as we started already kind of talking about, is we can use this to identify relationships. The more DNA you have in common with someone, the more likely, I shouldn't say that. The more DNA you have in common with someone, the more closely related you are to them. So for instance, if we were to run one of these gel electrophoresis tests between you and a sibling, you would have a lot of those fragments in common. If we run it between you and your parents, you would have a good amount in common, but less than you might have with your siblings. And if we run it between you and your cousins, you're going to have a lot less in common because you're not as closely related to them. And if we compare it between you and someone in Australia, it might be very, very different because you have a lot of degrees of separation in terms of relatedness. Now, you're both human, so you will have some of the basics of your DNA in common, but what this process tends to look at, it's aimed at the parts of our DNA that we could see differences in. So it's not going to look at the part of DNA that says, put the arms here, put the head here, make them a mammal. It's going to look at the parts that would signify differences, such as the genes for skin tone, certain slight structure variations, height, maybe blood type, things of that nature. All right, so I got a couple examples. So let's look at this one first. So here we have the baby on this side, and we have mom's DNA right there. Now, if we look at moms and babies, we should see some similarities. So I'm just grabbing a blue pen. So if you notice, mom and baby have that one in common, this one in common, this one in common, this one in common, and this one in common. No, that one's a little bit higher, sorry. That one's a little higher than that one. So they have 4 in common out of mom's 7s. And 1, 2, 3, 4, 5. Sorry. And then out of babies, there's 4 in common with mom and 5 that are not in common with mom. So we can see that there's similarities and differences. Well, now what we want to do is compare babies' DNA to each of the prospective dads. So let's take a look at this. No, 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 no. Yes. All right, so baby and possible dad 1 really only have one of these sections in common. So a lot that is not in common and very, very, very little that is. As a result, probably going to say this guy is doubtful to be the dad. All right, well, let's check out dad 2. Now the blue lines are just where I'm putting where baby's DNA is. 2. Got 1. All right. Possible dad 2 only has 1 section in common. So not a very likely candidate for being the baby daddy. So we got that one. That one. Now I'm looking at the third guy. Well, if we look, dad 3 has 1, 2, 3, 4, 5 sections in common with baby. So there's a lot more parts of the DNA that's in common with dad and baby, meaning that that is very likely to be the father of this baby. So that's one possible example of not just how this works, but how we analyze it and also what it can be used for. Another example would be murder suspects or even missing people. Let's say we have an unknown sample of DNA. So whether it's from a murder suspect or a criminal, or it could even be an unknown sample, and then we're trying to figure out, maybe it was someone, we have 3 missing people, and we found a sample of DNA that might belong to one of them. We can try and use it to identify who that person is. All right, so we run it, we have our fragments. Let's take a look to see who could potentially be the suspect in this murder trial. All right, so grabbing my little marker again. Boop, boop, boop. All right, so let's take a look at this, shall we? All right, so no, yes, no, 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 yes, no. Okay, so suspect 1 has 2 lines in common. Ah, yep, 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 yep. Oh, look at that. Suspect 2. All the lines are the same. Let's just double check suspect 3 just to make sure. No, yes, yes, no, no, no. Only 2 again. So you see how the lines all match up between the unknown sample and suspect 2? The reason why that happens is because the DNA came from the same source. Your DNA is unique to you, unless you have an identical twin, but that's a whole other issue. So it's unique to you. So if I take a sample of my DNA and then another sample of my DNA and I run them, it should look exactly the same. And that's what is going on here. So we have an unknown sample from a crime scene, and then we're like, this person right here, they might be the criminal. So we take a sample from the suspect. Well, if it turns up that they're the same, then that means it came from the same source, which means suspect 2 is our criminal. All right, so we talked about how we can use these in terms of figuring out, where did the cat go? Relationships or even identifying individuals. But we can also use this in a different sense, similar to the relationship, but a little bit on a larger, broader scale. We could also use gel electrophoresis in terms of comparing different species to figure out how closely related they are. Now, you might have heard that, we are like 99 or 98.9% genetically identical to chimps, I believe. And we're about 50% genetically identical to bananas. The reason why they're able to figure out those percentages is because they've been able to compare the DNA of different species. And from there, we're able to figure out how closely related we are. Now, the reason why we might want to do this is, let's say that there's a brand new species that was just discovered. And we want to know how to classify it. And if we want to know how to classify it, the best way to do that is to figure out what other species could it potentially be related to. So I have an example of that as well. All right, so let's say we have a brand new species of trees. Now, it has similarities to an oak tree, maple tree, a white pine, and a cherry blossom tree. So what I've done is I've taken DNA samples from oak, maple, white pine, and cherry blossom trees, and I ran them through the gel electrophoresis along with a DNA sample from the new species. Well, now I can compare the DNA samples to see, okay, how closely related is this new species, and how should I classify it? What kind of tree is it most like? All right, so let's start off with oak tree. So, no. Yeah, 1, 2. It's only got 2 sections in common. All right, let's try the maple tree. Yes, and yeah. All right, so it's got a lot in common with the maple tree. Let's look at the white pine. See, no, yes. No. 2 in common with the white pine. All right, let's try the cherry blossom now. Yes. No. Yes. All right, so by looking at this, we can see that it's got a lot of DNA in common with the maple tree. A lot of it. Now, is it genetically identical? No, it is not the same as this particular maple. Maybe it's a red maple. I don't know. But it's not exactly the same. But given how much DNA it has in common with it, we can say that it's very, very closely related. So it may not be this particular species of maple, but it might be a new species of maple tree. And we can say that because look at how much DNA there is. A lot of DNA in common means a very, very close relationship, as opposed to these others, which only have very, very little in common. That means that it's a much farther relationship, a much farther genetic relationship. Sorry about that. All right, so that's gel electrophoresis, pretty much in a nutshell. Now, there are, or is, bad grammar. There is another name that gel electrophoresis goes by. It's also called DNA fingerprinting because it's looking at these unique sections of DNA, kind of like how your fingerprints are unique to you. They're looking at these unique separation, these unique fragments. And apart from someone having an identical twin who is genetically identical to you, there would be no, or there shouldn't be anyone else with the same DNA. So that's why we like to use these in crime shows and actual real life crime fighting and missing person cases and things like that. Well, I hope this was informative. I hope you enjoyed it. And until next time, you guys, stay cool, stay awesome, and stay healthy. All right, you guys, take care. Bye-bye.